Okay, so today we're going to talk about rotational dynamics, which includes torque and rotational inertia. We talked about inertia in linear motion. What was the measure of inertia in linear motion? Mass, right. The measure of inertia in linear motion is mass. Well, we have to find an equivalent for rotational motion, because in rotational motion it matters where the mass is located. We can't just assume that it's a single point, which is what we did when we were doing linear motion, or translational motion, as it's otherwise known. So we know Newton's second law, and now we want to find the rotational equivalent of Newton's second law. So we can substitute the torque, which equals the radius times the force, and the tangential acceleration is r times alpha, the angular acceleration, right? If we put that in, what we obtain is this, that the torque equals mr squared alpha. This is the equivalent of Newton's second law. But it actually simplifies a little bit. We now look at this thing here. This is for a single point, like shown over here, single point mass. But what if what was happening was you had an entire disk spinning around? Well, what you'd have to do is you'd have to add up all the little masses going around here, right, all the way around, to find the total mass equivalent for this. And so what we do is we do just that. We say, okay, we're going to have a torque associated with each little piece of mass all the way around, and that's the sum of those times this. This is actually at a point where we get into the need to use calculus, right? There is no real easy way to do this in algebra. And next year, when you're doing calculus, you'll understand how it is you can go about coming up with solutions to problems like this. So, this quantity, I, which is sigma mr squared, is called the rotational inertia, also known as the moment of inertia of an object. Right? It is the equivalent of mass in rotational systems. It plays the same role that mass plays in linear or translational systems. Okay? And so what we can do is we can write this, the sum of the torques, or the net torque, is the sum of these mr squareds times the acceleration. We write it as this. The net torque is equal to the moment of inertia times the angular acceleration. It's now looking very familiar, right? If you like, this is Newton's second law for rotational motion. As I just noted, the distribution of mass matters here. We can no longer ignore that we've got an extended object, that is, that it actually has physical dimensions, like we do in translational motion. In translational motion, we're always looking at the center of mass, right? But in rotational motion, we can't just look at the center of mass anymore. So, the two objects have the same mass, but this one here has a greater rotational inertia. The reason being, around this axis at least, it has clearly a greater rotational inertia. You could imagine an axis like this, and then we'd have to do the calculations to see which one had the greatest rotational inertia around that particular axis. Do you follow me what I'm saying when you could have an axis down through here and you could be spinning it? It's like spinning a coin, right, on top of a desktop. And if you had this one spinning around, exactly which one has the greater moment of inertia would depend on the exact geometry, and we'd have to calculate that. So, we're going to solve problems in rotational inertia or rotational dynamics. It's pretty much the same thing that we have to do for dynamics in linear systems. You draw a diagram, you decide what the system comprises. Draw a free body diagram for each object under consideration, including all the forces acting on it and where they act. Find the axis of rotation. Calculate the torques around it, i.e. the forces, right? The rotational forces. Apply Newton's second law for rotation. And if the rotational inertia is not provided, you need to find it before proceeding with this step. In this case, you have a table of values you can look up, which are derived from calculus for different object geometries. Okay? Apply Newton's second law for translation, or linear motion, and other laws and principles as needed. Solve, and then check your answer for units and order of magnitude. So let's look at an example. We have two weights, here and here. One has a mass of 5 kilos, the other one has a mass of 7 kilos. And there's a rotational axis coming down here. They're separated by 4 meters, and this axis is halfway in between. And we're assuming they're connected by some sort of rod which has a negligible mass. That is, it doesn't come into the calculations here. We're asked to calculate the moment of inertia of the system when rotated around an axis halfway between the weights. It's a very simple system because we're assuming these are point masses, but they're extended because they're on this rod. So, both weights are the same distance, 2 meters, from the axis of rotation. This is where center of mass understanding becomes important from Chapter 7. For those of you who haven't done that, you might want to do that. We have the moment of inertia is the sum of the masses times the radii squared. So we have 5 kilos times 2 meters squared plus 7 kilos times 2 meters squared. Just 20 kilogram meter squared plus 28 kilogram meter squared, or 48 kilogram meter squared, is the moment of inertia for that system. Let's have a look at a slight change. Now what we're going to do is put the axis of rotation down here. Right, so it's sort of swinging around like that, but around that axis. Now, the radius to the 5 kilograms is 0.5 meters. The radius to the 7 kilo mass is 4.5 meters. Again, we're going to calculate the moment of inertia of this system. Again, we're looking for the sum of the masses times the radii squared to get the moment of inertia. So that's 5 kilos times 0.5 meters squared plus 7 kilos times 4.5 meters squared. That's 1.3 kilogram meter squared plus 142 kilogram meter squared to give us a moment of inertia of 143 kilogram meter squared. Clearly, since moment of inertia is the equivalent of mass in the linear system, the moment of inertia tells us how much an object is going to resist changes in its rotational motion. Just like mass in a linear system will tell us how much an object is going to resist changes in its motion. So if we compare this scenario where the axis is out here to the scenario where it was in the center, which one is going to provide the least resistance to changes in motion? Can anybody tell me? Yeah.
One's in the center.
Yeah, the one that's in the center. Because the moment of inertia is larger here. When the moment of inertia is larger, it resists changes in motion more than the one that has a lower moment of inertia. Just as it happens when you've got normal linear motion. So the example illustrates two important points. First one, the moment of inertia, that should be of, not if, for a given system is different for different axes of rotation. So it's not just a simple matter of looking at the shape of the object and saying, aha, that's a cylinder. I know what the moment of inertia for that is, and plugging it in. You've got to also take into account where is the axis of rotation. And the mass close to the axis of rotation contributes much, much less to the moment of inertia than mass which is further away. So this now starts to explain why, if we have two hoops, one of which is made of steel and hollow and has all its mass in the ring, and another one which is maybe a solid block of wood of the same dimensions and the same mass, it explains why the wooden block will get to the bottom of a ramp first. Because the rotational inertia to get that one going which has all the mass in the outside is much greater than the one where the mass is evenly distributed through it. So for most ordinary bodies, the mass is distributed continuously, and the calculation of the moment of inertia requires the use of calculus. You have to break it up into little bits depending on the geometry. And in fact, if you have a look in your textbook, you'll see this table, and I will give you this table in any quiz I give you. We have a thin hoop. The moment of inertia is given by the mass times the radius squared. Thin hoop means we can neglect the thickness of the ring itself. Here's the axis here. The axis is through the center and it's rotating that way. Here we've got the same thin hoop, right? And we've got an axis going down this way, so it's sort of flipping on its side. We've got something a little more complicated, where W is the width of this thing, right? 1/2 mr squared plus 1/12 mw squared. There's no way you can be expected to remember this. Once you've done some calculus, you can probably fairly easily derive it. A solid cylinder going through this, 1/2 mr squared. A hollow cylinder. Now we have to take into account the fact that it's an annulus. A uniform sphere, 2/5 mr squared. A long uniform rod, axis of rotation around the center, or long uniform rod, axis of rotation around one end. You can see them a little more clearly here. There's quite a difference in the moment of inertia. But you can see that where you've got something that's more balanced, you always have, in terms of where the masses are, you always have less or smaller moment of inertia. Okay? So let's have a look at another example. A force of tension is applied to a cord wrapped around a pulley of mass 4 kilograms and radius 33 centimeters, shown over here. The pulley is observed to accelerate uniformly from rest to reach an angular speed of 30 radians per second in 3 seconds. There's a frictional torque at the axle of 1.1 meter newtons. See, we're starting to take into account the fact that things aren't frictionless on moving pulleys now. We start to add in some more complication now that we can start thinking about how it works. And the pulley is assumed to rotate about its centre. I haven't shown the frictional force since we're only given its torque. Okay, we can calculate the moment of inertia from this. Since from the measurements given, we can determine both the net torque and the angular acceleration. Net torque is the applied torque due to Ft minus the frictional torque. We assume counterclockwise is positive. So we have this radius times the force minus 1.1 meter newtons, or 3.85 meter newtons is the net torque. The angular acceleration, alpha, is the change in angular speed over the time, or 30 radians per second minus 0 over 3 seconds, or 10 radians per second squared. And so the moment of inertia, because it was net torque equals I times alpha, we'll just move this over. I equals sigma torque over alpha, sigma tau over alpha, 3.85 meter newtons over 10 radians per second, or 0.385 kilogram meter squared.